Yeah, hi. Good evening. Good evening, everyone. So, welcome to the open session, week 9. Before starting the session, I just wanted to ask you that regarding the quiz two. So, if you have any issue regarding the quiz two, please just let us know. Uh, have anyone have any issue? Because of that, we have also asked in the that forum, but we received just now. We received one that complaint or issue. So, any doubt in answer key or any question?
Sir, not regarding that, but can you quickly explain the OPP pattern or syllabus?
OPP patterns, yeah, that we will discuss definitely. Yeah, before that quiz too, any issue is there? If
Sir,
anyone.
that stable sort question, I mean, it's not a complaint. I just wanted to know how it
That is
works.
fine because we also noticed that. Yeah, that heap sort is actually not stable. So that last option should be correct. So we have noted down this. Okay, any other?
Okay, sir. Thank you.
Hmm. Okay. Okay, so that this is the only issue we have received till now. We have received other also by the form, but that are not looking valid. So because of that, we have posted one post in the forum, so we can discuss if anyone have any doubt. Okay, so yeah, so that we will correct it. This one question, so we will include that last option in the correct option. Otherwise, I think all questions are okay. Okay.
Sorry,
Sir,
sir,
there is
just question about which question
Yeah.
you are talking
Sorry, who's talking? Ashish.
Yes, sir.
What you're talking?
Sir, I have joined just now. About which question you
That
were discussing?
quiz two actually. If any question you have any doubt regarding the answer or any question wrong, something wrong in the question or answer.
No, no, no. You just mentioned that we will implement one more option as a correct option. Which question you
So
are
there
talking?
is one question. So let me share you one. Someone is posted in the forum also
Okay,
that.
okay.
So that heap sort based question in the quiz two. This one. Yeah, this question if you remember. So here, which statement is true for the heap sort? So this last statement is mentioned that heap sort is not stable sorting algorithm. So this is also true. Okay, heap sort is actually not a stable algorithm. So we will mark this as a true statement in this question. Okay. So this is the one valid issue we found till now. If anyone have others, please post on the forum. Okay. So we have also post one this thread, quiz feedback or any discrepancy if anyone have.
Sir, one more question related to that greedy algorithm. That coin question is there.
Coin question was there. Yes. So what was your doubt?
So, wait, put it down.
If you have that question, if you can share. Let me open from the portal 1 second. Answer key. Mock unit. Mock unit. Answer key. That quiz 2% paper. So DP degree and diploma. Yeah. So all actually QP was same. So in the all shift. So I'm opening one paper. PDSA. So I think you're talking about this point person. So that was the last question. I think. Yeah, this one. Na?
Yes, yes.
Huh,
Oh,
so
okay, sir. Okay, sir. Actually, it was my mistake. I thought
okay,
some
okay.
the
Then
first option was incorrect. I thought. No.
yeah, then fine. Okay. Okay. Okay, so we will update this in the answers, and after that, we will your result actually will be released. Okay, so today is actually week 9. Yeah, regarding the OPP actually things. So OPP had the syllabus till week 9. Okay, and you will get 4 programming problems of equal weightage. So each problems will contain 25 marks, and the duration of this exam is 2 hours. Okay, sorry.
And sir, suppose there is a program relating Dijkstra, BFS, DFS, anything. So
Hmm.
we will get the pre code for that.
No, if problem is directly based on the Dijkstra algorithm without doing any other task, so then at that time you have to write the Dijkstra algorithm code. Okay, if problem have some additional task apart from the that algorithms. Okay, so maybe algorithm is required, but after that additional task is also required. So in that case, that algorithm will be given to you.
Okay.
Okay, but if problem is directly depends on the algorithm, so like BFS algorithm, you just write the BFS code and you will get the answer. So if problem directly depends on the algorithm, in that case you have to write the complete solve code for that algorithm.
Yes.
Okay, yeah. So
Sir,
yes, yes.
sir, can you share, tell me some topics like that we should
So
prepare?
that I am discussing now. So
Okay.
what topics are important for the OPP? I have also posted on the forum, and so you can expect one problem from that linked list and sorting these topics. Okay, so linked list is important. You should know how you can perform some operations like traversing the linked list, deleting the node from the first position, last position, and some reverse that linked list and swap the elements like this. So basic operations on the linked list. Okay, so any PYQ for OPP or any website. So PYQ actually we not release the OPP question paper generally, but we have already included many of the questions from the OPP in our assignments or live coding sessions. So live coding problems, there are many questions are actually taken from that PYQ, and we will also release some OPP that mock set. So in that question, that questions are also belongs to the previous OPP. Okay. Otherwise, we are not releasing the complete term-wise questions file for this OPP exam. Yeah. So, yeah, first topic you can focus on the linked list. You should know properly the traversing part and some update part of the linked list. Okay, like remove the element from the any position, start position, last position, like this. If some input is given. So linked list is the main important. Other things is some binary search algorithm related problems. Okay, so we have already discussed many some problems in the assignments which can be solved using the binary search concepts. Okay, so you can revise them. And apart from that, yeah, like IITM Rex, yeah.
So, just a doubt from the exam point of view.
Hmm.
There was a question for heap sort. So, is the fourth option correct or
That
wrong?
is true. That is true. That is correct.
Yes, yes, I had asked it in the discourse as well.
Oh, you mentioned that post. We have just discussed that things uh,
Yeah.
in the initial of this session.
Oh, okay. Sorry, sir. I joined in late.
Okay,
That's
okay.
what I
So
have a
we have
question.
clarified this. That option is correct. We will update that.
So, the entire question I'll get right? If I get all the three options right?
So we will include that last option in the correct answer. After that, you will get the marks. So if your all three options are correct, you will get full marks. Otherwise, some partial mark maybe someone get. So this is MSQ.
Okay, sir. Yes, sir. Yes,
Yeah,
understood.
those, yeah, who select the part of the correct option, so they will also get the partial marks.
Yes, sir. Okay, sir. Thank
So
you.
yeah, that we will update. Yeah. So that things we have discussed in the initial things. If anyone have any issue, and I have already seen your post in the forum, and so we will update this. Yeah. Okay. So next thing is yeah. So I have mentioned that linked list and binary search and sorting. You know that sorting are basic, so you can simply use this sort function of the Python library. So that is not much required. You can directly use if required. Apart from that, one problem will be based on the graph algorithms. Okay, so here in the graph algorithm, you have week 4 and week 5 content. So in this, what you can focus, so you can focus on the BFS algorithm. So some problems may be asked from the BFS, like finding out the component, number of components, and connectivity. Okay, so in this way, some problem can be solved using this BFS. So BFS is important. And topological sort. So some dependency problems can be solved using the topological sort algorithm. So you can focus on this topological sort algorithm. And week 5, any one of the sorting that shortest path algorithm you can just learn. Okay, so if suppose if any problems asked based on the shortest path, okay, so you can apply any of the one like the Dijkstras algorithm or Bellman-Ford algorithm or Flood-Warshall algorithms to return this information. Okay, so just remember at least one of the shortest path algorithm or at least one of the minimum spanning tree algorithm, either Kruskal or Prince. Okay, so these four algorithms are important. Okay, and related things you can disclose that what are the application can be asked related to these algorithms. So these four algorithms are important for this graph problem. Okay, and next one topic is that greedy algorithms. Okay, so greedy algorithms, you can figure out that what type of, so after some applying some sorting things, you can follow some approach to perform the task. So you can practice on some greedy algorithms, and one problem you can expect from dynamic programming.
Sir, are you sharing your screen?
No, I am not sharing anything. I'm just talking. Okay, yeah, my screen is shared, but I am not showing something. Okay, so that things I have also posted on the forum. You can see on the forum. This is as I mentioned what he mentioned actually. Okay.
Sir, sorry, I just joined 2 minutes back. I mean, just now. So you are saying one problem from the shortest path, one from the minimum cost spanning tree, and one
No,
from
no,
the
no, 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 no. One problem from the graph. I'm mentioned this. So I've mentioned this PDSA syllabus pattern. Yeah. So you can see I've mentioned this. You can focus on these area: linked list operations, binary search concept based problem. One problem definitely from the graph. Okay, so that maybe based on BFS or sometimes DFS, but not DFS is not too much important because that component connectivity you can also check from the BFS, or cycle things you can also check. Finding component, yeah, this is the application. Okay, so topological sort. So some dependency based problem you can solve using this topological sort. Shortest path problem, you can just learn any shortest path algorithm, any one of them, like Wellman-Ford or Dijkstras, like this algorithm, and any one minimum spanning tree algorithm which you can find easy. Okay, so that Kruskal or maybe Frames. So one problem definitely will come from this part. Okay, and one problems you can expect from this dynamic programming problem. So you can practice some uh, not too much hard problems. Okay, so the problems which are very uh, that moderate or easy level, we can say that that you have already seen that type of problems in your assignments and live coding sessions or mock questions. So level will be
Dynamic programming based on week 9, sir.
Week-9.
Okay.
Okay, and greedy problems, maybe some problems will be based on, you can apply your logic. So but the I'm just discussing about the concepts. Otherwise you can apply any other logic. So like dynamic programming can also be solved using some recursive methods. So if you found the recursive method easy for them, you can also apply. So we are not restricting them. Sometimes we tested only this binary search based problems for the complexity actually. Okay, so you have to write the binary search solution, so that you have to write the solution of log n complexity. So in some problem we will test this time complexity, and that will be mentioned in the question statement itself. Okay, otherwise you can also apply your own any logic. So but these are the area where you can focus more and you can practice more. Okay, and I have shared one sheet that where some that problems are taken from these competitive platforms, and that I have shared that sheet with the TA. Okay, and so TA now will start the discussion of on these programming problems only in the remaining session. Okay, so TA will share that sheet with you, so you can practice the problems related on these topics on the competitive platform like Lead Code or Geeks for Geek on this topic. So some additional resource actually that he will share actually. Okay, so yeah, so and if you have done all the programming assignment till now till week 9 by your own in assignments or live coding session, if you have done, definitely your OPP exam will be easy. Okay, so not too much difficult. But if you have not done anything, okay, and if you have not practiced properly, then that definitely it will be difficult. Okay, so yeah, practice on these area. Yeah, any query related to this now?
So what's the minimum we have to score for the OPP?
No, there is no any separate criteria for the PDSA OPP. Okay, this
Okay.
contain only 20% weightage in the total score. So there is no
Okay.
separate passing criteria for this.
Okay.
Okay, so there is no that. So you can just give this exam to just score maximum marks. No, just not passing for this. Okay, so yeah, any doubt, any talk, any query, clarification regarding the OPP?
Sir, so no questions on BST trees, nothing.
That type of longer implementation, so which you have seen in week 6 and like AVL tree and that type of generally we not ask. Okay, so you can skip that. Okay.
Yes.
Sir, there is one question in PDS.
What
Sir, I have problem in one question.
you have solved?
Yes, yes, sir, I try.
So what you are asking?
Sir, I'm asking quiz to last question.
Quiz to last question. Okay, that what's your doubt? That coins question you are talking?
Yes, 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 sir.
So what's your doubt?
Sir, I'm asking that which option is correct? How much we find which option is correct and which is wrong?
Okay, so I have just shared that. I'm opening again. This one. This one, na?
Sir,
Yeah. Is it visible?
no, sir.
Yeah,
Yes, sir. Yes, yes.
Okay, so this question, na? This coin
Yes, sir.
question. So here some strategies is given, that greedy strategy given to solve this question to get the optimum answer. What is the problem? We have some that k coins, okay, and we have infinite number of the each coins, and we have some amount value, and we want to get that amount value with the minimum number of coins. Okay, so here
Yes, sir.
some options are given, and strategies that greedy method is also mentioned, that we will follow this method to solve this problem. Okay, what that method is saying, that just always pick the maximum value coin. Okay, and just try to complete the amount by the maximum number, the maximum value coin. If it is not possible, then select the second maximum one. Okay, so in this way, just try to complete the amount. So here, if we follow, so here asking that which of the following option is a counter example to prove that this given greedy strategy is not optimum. Okay, so here we will apply this greedy method on each option, and we will figure out that we are getting the optimum answer or not. Okay, or any other optimum answer is also possible for this. So let me just cut this and explain one second. So, okay, so here you can see what option we have. So first option, we have this 1 2, 8, 9, 5. Okay, 9, 5, and 10. These. So we have the amount x equal to 13. Now 13, how we can that get from these number of coins? So what is the maximum value of coin is 10. Okay, and we can take only one coin from this value, or if we take two, then we will get the higher value from this 13. So we can take at least one coin of the 10 value. After that, what is the remaining amount? We have 3. Okay, so for 3 we cannot take this second maximum. Okay, so because this is the larger, now third maximum, then fourth maximum, then we can take only this 2. Okay, so that means we can take one coin from this 2 and we will get 2 value. Now what is the remaining amount is 1, so we can take this value 1. So 1 into 1, 1. So now you are getting total 13 value. So if we are following this greedy strategy, we are getting 3 answer for this. So 3 coin we require at least. Okay, but are we getting any another optimum answer for this? So you can see, if we pick one coin from this 8 and one coin from the 5 value, okay, then you are getting the total amount 30 by 8 plus 3, sorry, 5. Okay, so now in this case only 2 coins are required if you are picking this value. So that means here by the given greedy strategy we are getting 3 answers, but optimum answer is 2. So that means this greedy strategy is failed for this option. It is not giving the correct answer for this option. So because of that, this is a counter example to prove that this greedy strategy is not optimum. Okay. Now for second option, if you get the 25, so then that means you can pick 2 coins of the 10, and after that 1 coins of the 5. So total 25. So total 3 answer is there. Now in this input, you will get, this is the optimum answer actually. 3. You cannot get any more optimum answer from this. So this option is not a proper counter example. Okay, same for this 15. So for 15 you need 2 coins for 7 and one for, so total 3 coins are required according to this strategy, and this is the correct answer. Okay, so you will get the same 3 optimum value and you cannot get any another option, okay, which is less than this. And for this next this example, you can see we need to get 35, and by the greedy strategy we are using this 15. Okay, so 15 into 2, 30. So 2 into 15, and after that we are remaining 5. So we can only use this one coin. Okay, so 5 times. Okay, we cannot take any value, so like 10, 7, 6 we cannot take by this strategy. So 1 into 5, 5 into 1. So total coins are 7 required. But can we do this in the better, by the better option? So you can see 7, and we can take 5 coins of the 7, you will get this 35. So that means we are getting 5 coins, which is more optimum from this value. So this is also a counter example. So this is correct. Okay, so in this way we need to check like this. Okay, after first things we will just use this greedy strategy to get the answer. After
Sir, can you explain 35 again?
So 35, if we are following the greedy strategy, so we will always pick the maximum value. So 15 we are picking, and we can take 2 into 15. That means 30 value is covered. Now 5 is remaining, so 5 we can cover by the only this one value coin. Okay, because we cannot take 10, we cannot take 7, we cannot take 6, because all are greater than this 5. Now we can take only that 5 number of coins with value 1. So total 5. So now we have 35 value with total 7 coin by this greedy strategy. But you can also achieve this 35 value by the 5 coins of 7 value. 35. Okay, so this here we need only 5 coins, but our greedy strategy is giving the answer 7 coins is the minimum. So yeah, this is the counter example, we can see that. So this is not actually optimum strategy. Okay, so in this way we need to validate this.
So this 35 is optimum strategy, no? The one which you told now.
No, 35, if we are following this given greedy strategy, we are getting 7 number of coins. So you can see we are getting 7 number of coins. But if we are looking the option, we can also achieve this amount by the 7 into 5 number of coins with the 7 value. So total 35 value. So this 5 is minimum or 7 is minimum? 5 is minimum. So that means that approach is not giving the optimum correct answer.
Sir, here we are taking 7 coins. So 2 coins, 15 rupees, 30, and 5 coins of 1 rupees, is it?
Yes.
That restriction is there.
What
No.
we are doing, we are just picking the largest amount coin first, okay, and we are trying to cover our value by that coin, okay. So we can take any number of coins from any value. So here we can take maximum 2 value, the 2 coins, okay. So it will cover 30 amount. After that 5 value is remaining. So for remaining 5 value, you cannot take the coin with 10 value, which is greater, okay. So you have to skip this. And 7 is also greater, you have to skip this. Then 6 is also greater than to the 5, so you have to skip this. Then 1 is the only smaller coin, so you have to cover your value by this one value coin. So 5 is remaining, so you need 5 coins for this one value. So because of the total coins are
Yeah, I got it. So the other thing what you are saying is there we can choose a lesser value coin and still can get that.
Yeah, so if we are taking 5 coins of 7 value, we are also getting this amount, and this is the optimum answer for this, okay. That means we are achieving our
So
answer.
you can do it with 3 coins. If you take 2 10s and a 15, you can do it with 3 coins, right? That will be the optimum.
That is more optimum. Yeah, this is also one counter example. Yeah, correct. So that 2 coins for 20, 20, and then 35. So 3 coins are also required. So this is more optimum answer. So that means our greedy strategy is not giving the correct answer for this option, this input. Okay.
Sir, can you explain the question in which we have to find the maximum possible weight that a minimum weight spanning tree can have?
No, here it is mentioned that consider the following greedy strategy.
No, sir, I'm asking about different question.
Different question means?
Another question.
Which one?
The one question in which we have to determine the maximum possible weight that a minimum weight spanning tree can have.
That one. Okay. So that type of question we have discussed in revision session. I'm not sure you have joined or not. Okay. This one, na?
Yes, sir.
Okay. So very similar question we have discussed in our this revision session also. So that here what is given, we have 5 vertices. Okay. So 5 vertices we can give any name. So like A, B, C, and D, and now E. Okay. Now we have 10 edge. Okay. So that means this is a complete graph. It is given also. This is a complete graph with 5 vertices where the weights value are also given, but you don't know how these weights are actually assigned to the graph. Okay, so there are multiple possibility we have. We can arrange these weights on the different 10 edge in the graph, input graph. So among all these, we need to figure out that the maximum possible weight that a minimum spanning tree weight is maximum possible weight that a minimum weight spanning tree of G can have. So we need to figure out the minimum spanning tree first. Okay, so minimum spanning tree for this type of graph where we have this weights, okay, total 10 weights, and we need to figure out the maximum possible weights for any input graph, any input possible graph with this type of condition. Okay, so how we can figure out that? We have discussed this question with 4 vertices. Okay, and now this question is with the 5 vertices. So that means suppose if you follow the Kruskal algorithm, so Kruskal algorithm always pick the minimum edge weight. Okay, and if you are picking first edge, so definitely according to the Kruskal algorithm, we skip the edge if it is creating a cycle. Okay, if it is not creating a cycle, then we will include that into the minimum spanning tree. So how we can figure out that if we are picking the first edge with one weight, okay, so definitely it cannot create a cycle. One edge cannot create a cycle in the graph. Okay, now we are connecting this edge in our graph, so you can connect in anywhere. So like if you are connecting here, okay, so this edge cannot be create cycle, so that means this weight, this edge definitely will include in your minimum spanning tree. Now second, if you pick second edge in the graph, that will also not create a cycle. Okay, you cannot create a cycle with two edge in the graph. Okay, so that means the second edge will also be included in always. So this means these two will also be come in this graph, and I'm assuming that suppose this is coming here. Okay, because here our goal is to find out the maximum possible weight for any minimum spanning tree for this input graph. Okay, so now this definite this is also, this will also be included. Now the next question is this third one. Okay, so if we are including third edge, so it may be create a cycle or it may not be create a cycle. What are the forms? So suppose if we are getting this edge 3 in any another node, so like this, it is coming here. So this 3 will be included in the spanning tree. But our goal is here to find out the maximum possible weight. So what we can assume that if suppose this is creating a cycle, so how this can create a cycle? If suppose this is coming in between this, okay, if these 3 weights are coming in between, so we cannot select this edge. We have to move the next weight, and which is higher than this. So that means we will get some higher cost if we are skipping smaller value and picking the larger value for third edge. Okay, so here third, this we can skip by here, so this will not be included because it is creating a cycle in between these two edge. Okay, now we have to definitely, if it is, we are assuming that this is creating a cycle, so next one edge definitely will not create a cycle. Okay, because the all cycle edge are now completed.
Sir, why we remove third?
Because it is creating a cycle. If we are assuming that it connects C and B, okay, so in minimum spanning tree we cannot include this. It is creating a cycle.
Sir, we can assume that it can connect C and D.
So you will get a answer, but that will be the minimum possible minimum spanning tree. So suppose I am getting the what are the answer possible for that. So let's if you are assuming that I'm just removing this according to you. Okay. You are saying that this is now connecting here, correct?
Yes, sir.
Okay, now we are adding this in our answer. So for now, because this graph have only 5 vertices, that means we need only 4 maximum 4 edge to connect all the vertices. Okay, so 3 now we have connected. Now suppose if you are saying that if we are assuming this 4, if we add this 4 into like this, okay, it is also not creating a cycle. So now we got our minimum spanning tree, but what is the total weight for this? Total 3, 3, 6 and 10. Okay, so we are getting this one possible answer. Okay, suppose if our graph have like this, so A, B, C and D, E, and I'm talking about the input possible graph. Okay, so suppose this is 1, this is 2, this is 3, and this is now 4, and this is 5. Okay, and we have some remaining edge also, suppose like this, because this is a total connected graph, so all edges are there. So like this is also there, this is also there, total 10. So I'm assuming only this first 5. So suppose consider this now in edge input. Okay, so what edge will be considered? So A and B. Okay, so this 1 will be considered first, and then C, this 2 will be considered. Now you cannot pick this BC, okay, which have this 3 weight. Okay, in that case you cannot pick this. You have to move to the next greater one. So suppose this you are taking this now D. Okay, this is 4, and after that you have one edge like this E, and this is 5. Okay, so 1, 2, 4, 5. Now this is again another possible. This is also a minimum spanning tree. Okay, so I'm just assuming this 6, 7, 8, and 9 or any edge is remaining. So like this 10. So we are assuming the same condition. So we have the all weights 1 to 10 in the edge, and we have 5 vertices or 10 edges connected. Now, suppose if you are creating a minimum spanning tree for this input graph, then you have to pick these as only. You can pick only these as. So in this case, what you are getting 1 plus 2 plus 4 plus 5, total 11.
Sir, it should be 12.
1 2 3 4. Okay, yeah, 12. Fine. Yeah. Okay, so you are getting 12, which is more than. And question is asking what maximum possible weights that a minimum weight spanning tree of this G can have. So we are figuring out that what is the minimum possible value we can get for this type of input graph. Okay, so that means this is 10 is not the answer. Now 12 we are getting, but this may also be not the correct answer. So we are getting this 14. So what possible case for this? So one is, as we have skipped this A, suppose this A to B, this we are taking 1, and this C, like this is 2, and we are assuming that here we want to skip the smaller weight edge and we want to pick the greater one. Okay, but according to the input given conditions. So here that third, this 3 weight edge can be skipped only if this is connecting these 1 and 2. Okay, like this. So this is coming 3, so that will be skip actually. Okay, so we cannot take this. So in that case, now just assume that if any edge is that fourth edge, if 1 2 3, this is the input graph. Suppose if you suppose this, if your fourth edge is connecting between any other, so C, D and E, so that is B. Now you can connect any edge with this 4 weight, so 4 with weight 4 value with any of the another possibility. Okay, so apart from this, so you can connect between CD, DE, BE or AD, AE. That will definitely include in your graph, because your cycle is now creating in between, all edges are completed in between these 3 nodes, and this fourth next edge actually definitely will connect to the new node. Okay, so that will not create a cycle. So if it is coming in any place, so definitely it will include. So 1 plus 2 plus 3 we are skipping, then this 4 will include in your spanning tree. Suppose if I'm taking this situation, so if this is coming here, okay, so 4. Now next edge. Okay, so we are taking the edge number 5th edge, which have the value 5. So it may be create a cycle or it may not be create a cycle. Okay, if it is creating a cycle, so we will skip this and we will move to the next higher one. Okay, so what is the case where it will create a cycle? So you can see, suppose if this 5th edge is connecting these two, this one, then 5. Okay, now you have taken AB, AC and CD, and this BD edge is connecting with weight 5. You cannot take this, you have to skip this. And if it is not creating a cycle, so you will get a final answer. So 1 plus 2 plus 4 plus 5. So that is actually 12, we have already seen. Okay, but we are assuming that in which case it will create a cycle. So where we can skip this and we will pick the next maximum. So you can see in this case, it will create a cycle. So between this B, A, C, D. Okay, so we cannot pick this. And after that, so we are not picking this, we are skipping this. Now the next S with value 6. Okay, so definitely it will come, it will not create a cycle after that. Okay, so it will not create a cycle in any case. So if you are connecting this as like
with CD, it will create a cycle. You can skip that too.
Where?
If it's AD, it will create a cycle, right?
A?
If it's A and D.
A and D.
Yeah.
Yeah, that is correct. Okay. Yeah, you are correct. So yes, yeah, this is A and D. Yeah, correct. So this 6 is also can create a cycle. Yeah, correct. This is A and D. So that we can also not.
Can you explain again A and D? What?
Sorry.
Sir, what are you? How 6 can create a cycle?
So I have also making the input graph now. So you can see 3 we cannot pick. If 5 is connecting between this D and B, we can also not pick. Suppose one more edge is also possible in between this. Okay, so this is contains like 6 weight. Can you pick this? If you have selecting this 1, 2, 4.
Okay, sir.
Okay, it will not create it. It will create a cycle. So we cannot pick this also. And okay, so now next way, now all possibilities are completed between these four edges. Okay, so now this is become a complete graph. Now we cannot connect any another edge in between. So definitely the 7th edge with weight 7 value. Okay, so that will be come with this E. Okay, either BE, DE, CE, or AE, like this. Okay, so that definitely will not create a cycle, because the possibility of the cycle is now finished with these 4 nodes. If you are connecting any edge between this with E, it will not definitely create cycle. So suppose if you are taking this like BE 7, so that will include in your MST, and that is the maximum possibility for the minimum spanning tree. If your input graph contains this type of situation, okay, and now you can connect the remaining edge in any position, and if you try to create a MST for this, you will get this 1 plus 2 plus 4 plus 7. Okay, so total 14. This is the maximum possible weight for any minimum spanning tree for this type of input scenario. Okay.
Sir, so in this question we have to maintain the order. How we giving
So
the
you have to assume the situation actually, which actually smaller as we can skip in which case. So we have to focus on the cycle things, and when actually the cycle is possible, so that we can ignore with the smaller weight, and then we will move to the next weight. Okay, so here 3 we have skipped at the first time. Now when only this is the only one possibility with when it can be created cycle. After that you can see next this 4 we have definitely take, because it is connecting to the next vertices. Now till now you can see these 3 vertex can contain only 3 edge maximum, and after that next edge definitely will connect a new vertices. And if our edge is connecting to a new vertices, so it will not create a cycle. Now when we included this, so now the possibilities increases for the cycle for next edge. Okay, so now you can see BD can also be created cycle. Now AD can also be created cycle. So that means we have to skip next to edge. We can skip this next to edge by this. After that it become a complete graph. In next edge you have to definitely connect to the next new edge or vertices. So that you have to take for your minimum spanning tree. Okay, so in that case we are getting this 14.
So we have to first fill the edges which are diagonals in this ABCD. Sir, why?
Sorry?
Sir, first why we have to fill the diagonals?
If you not filled, you will get the smaller answer. Now we have seen that if you are not filling in this way, if and you are including all the smallest edge directly, so you will get the answer like 10. You have already seen, but that is one possible answer. Okay, another answer we have seen 12. Now this is the third possible answer we have seen 14. So among all these, which one is the maximum? 14. Okay, so which here we are looking the possibility, maximum possible answer for this.
Okay, sir.
Okay. Yeah. Okay, it's fine. Okay, now if you have any or other doubt, please post on the forum. We have created one the thread for this. Okay, and we will discuss there. Okay, so this today week 9. Let's cover some things. So Week-9 is basically dynamic programming, and it is important for the OPPE exam purpose. And now the end-term exam, these 2 weeks are the new content. Okay, the remaining will be the same. So week 1 to 11, and you know that week 10 now there's no content, no new content in week 10, and week 11 you will get new content. Okay, so that will also be included in your syllabus. After that, week 12. Okay, so that string matching algorithms we will release, but that actually a extra content, not that will not be included in the syllabus for N term. Okay, so syllabus is only till week 1 to week 11, without including that string matching, that week 12 part. Okay, so now two new weeks are there, so to learn. After that, the interim exam will contain the questions from the each from week 1 to week 11. Okay, all weeks have approx with the similar weightage. Okay, so week 9 dynamic programming. This is now a new algorithm design strategy, and we will see what type of problems we can see and what is this dynamic programming. So any problems, if any problems can be that you can see this point. So any problems where solution to the original problem can be derived by combining solution to the sub problem. Okay, so if we can get the final optimum solution by combining the solution of the smaller problems, so that is one required things for the dynamic programming. And there are another two property we have required in the problem actually. That is one, that optimal substructure property, and that overlapping problems. So that means if we are that optimal substructure property is this one which is given here. Okay, so if what we can do, we can instead to solve the problem directly, what we can do, we can start with the sub problems. So that means we can start with the sub problem of that problem, and we can get the answer of the solution for the sub problem, and using that solution of sub problem, we will achieve the final solution for the original problem. Okay, so that is optimal substructure property. So if any problem can be solved in this behavior, so that means we can use the dynamic programming approach for that. Okay, another is of that overlapping sub problem. So that means if we are solving the problem by sub problems, and where we are solving the sub problems again and again multiple times in the problem. Okay, if any problems required to solve any sub problem multiple times, so that is called as a overlapping sub problem. So suppose you have the S1 P problem. Okay, and now this can be divided into sub problem like P1, P2, okay, P3, P4, P5. These are the sub problem of this problem. If we, so first optimal substructure property says that if we can achieve the final global optimum solution by using the solution of these sub problems. Okay, another property, during the solution of sub problems, we need to solve these sub problems repeat again and again multiple times. Okay, so if we have solved this P1, maybe in the another part of the problem we need to solve this problem again if this is required. Hello.
Can you please tell again?
So that first property, optimal substructure property, that is actually if any original problem P can be solved by the solution of sub problems solution. Okay, so this is the optimal substructure property. And
if I may interrupt, so is it something like the greedy algorithm? So basically we are
no, greedy algorithm is not like this.
There also we try to go for the maximum value and then try to solve it. Here also we are breaking it into multiple pieces and then
So here we are solving that problems okay, and sub problems, and we are getting the optimal solution for each sub problem. Okay, and using we will use this optimal solution of sub problem, and we will achieve the final global that optimum solution. But greedy is also similar to this, but that actually not guaranteed to the correct optimum solution, which we have seen in the coins problem. Okay, greedy looks like that works actually for the some problems, but you need proof for that. Okay, it may be fail sometimes.
So here you are saying if we break the main global problem into the local sub problems, this will always give us the best solution.
It will always give the final optimum solution for original problem. Okay. But greedy we require the proof. That is not guaranteed that sometimes you will feel that your greedy is working, but maybe it may be fail. for some cases. So you need proof for that.
Okay, sir, for the greedy algorithm, while explaining, you gave one example that something 31, 32 and the other one not working. If you recall, can you please repeat that example? I just wanted to get that once. You explained that in one of the lecture session actually.
Greedy.
Something you told that addition of three numbers is giving some 32 something optimum, but in the lower end something 12 or 14 we wanted to get and we did not get that, but we got it with a
So that
lesser.
one, now we have discussed this coins problem. No, suppose we have this some set of numbers we have, okay, and like 1, 5, 7, and 8, and 3, 2, that 10, like this we have, or suppose we have this type of number. So, and if you apply any greedy method for this, so that means you will sort this and you will apply some strategy to solve the answer. But sometimes in the problems you cannot achieve the correct answer, because you will get the answer by some any specific set from the given set. So maybe like we are figuring out the subset sum problem, okay, and we are figuring out the number of that's we need to figure out the minimum number of elements which we will get the final sum value, like this. If suppose if we are thinking we need total 13 value, okay, and we have this 9, like suppose this we have 9, okay, and here we will find out that what is the minimum subset we need to get this value 13 by any number of elements, okay. So here if you apply any greedy strategy, so like you will apply, suppose if you sort this and you pick the maximum one, like this 9, after that you cannot pick this, yeah, you can pick this 3. Before that you cannot pick anything, because 9 plus 8 will become 17, 7, 16, this is also greater. But then you have to pick this 9 and then 3, okay, so 9, 3, 12, then you have to pick this one, okay. So in this way, if you are applying any strategy to, like after sorting you are picking something, so that looks correct for some input, but here you can get this answer by picking this 5 and 8, okay, where the answer is possible by any possible sets for the input,
Got
okay,
it. Got
and
it.
you cannot that you cannot get the answer by just some specific strategy like sorting and just picking the maximum things and like this, and your answer may come from any possible input case, okay, input position or input sets. So that type of situation you cannot apply the greedy strategy. And here in this type of problems, that means if you want to solve this, so the naive approach is just try to pick all the possible combination, okay. So here what you can do, you can just pick one element, okay, check the answer, then after that two elements, so like 1 and 5, then 1 and 7, then 1 and 8, you can get, like, check this. So here you are checking the solution by all possibility of the set. But dynamic programming actually gives the smarter strategy where you no need to repeat the process actually. Okay, so what we are happening here, suppose if we are picking the sets, okay, we are applying the naive approach and we are trying to figure out the all possible combination, okay. And so in this way, if we are picking like 1 and 5, okay, and we are not getting the answer, so but we have solved this problem. 1 plus 5 is giving 6, which is not giving the answer. But in the another possible set, if you are picking like 1 comma 5 comma 7, okay, now you are again adding this value 1 plus 5 plus 7, but you have already done this 1 plus 5 before in one of the previous part, okay. So why you are doing this task again here? And suppose if you are picking the another set like 1 comma 5 comma 7 comma 3, so if you are just checking for this subset, you are getting correct answer, not same things. You have already added, you have already checked and added this part before, okay, and you have also added you have checked for this part, okay, and here in this problem, but you not get the answer. So why you are repeating all this addition again and again? Okay, so greedy, the dynamic programming approach actually store the result of sub problems and use that solution to solve the problem again. So suppose if according to the dynamic programming, if we have solved this 1 plus 5, in next time if we are including the 7. So we will not again add this part. We will directly get the result from this part, what result we are getting from this 1 plus 5. And we will add included in this. So 6 plus 7 directly. Okay. So that means we will use the solution of sub problems, and we will directly include in our that solution in our calculation. So that is called as a overlapping sub problems. So here you can see if we are figuring out the all possible sets to get this solution 13, okay, by naive approach, and we are trying to figure out the all with all possible combination. So in that case, if we have done this part, again we are doing this part here, again we are doing this part here, okay, this addition things. So that means we are repeating the same task again and again. Okay, we are repeating the same sub problems again and again. So this is called as a overlapping sub problems. Things. So if our problems looks like this, if it contains this property overlapping sub problems, or that means, or we have also, that should we confirm this our problem. So if we are we can start with sub problems. So suppose if our goal is something, and if we are finding out the optimal solution for the smaller problem of that main original problem, so can we achieve the final global optimum using the optimum solution of a smaller problem or not? So that is the optimal substructure property. So that two things is required in the problem. So to check, you have to ensure that things, if your problem can be solved like this way. So now here, this after this two property, we have this very common example to understand this Fibonacci series. Okay, Fibonacci series. Now we will see the different version of the solution for this. So one way is the recursive approach. So here recursive approach will figure out the all possible possibility of this solution. So like this, if you can see Fibonacci, that nth Fibonacci number. Okay, what is the nth Fibonacci number? How you can get this? You can simply take the recursive approach, and you can just get this. If n is less than equal to 1, return n. Otherwise, call the two previous value. Return fib rec n minus 1 and fib rec n minus 2. So this is now two recursive call in the every call, and if we are reaching at the base case, we will return 1. Okay. So here 1 or 0. Yeah. So now you can see the structure of call. You can see the structure of call this solution, recursive solution. Now this is the main call for fib 5. That means you want to find out the fifth element. Now this, after this first call, these two calls will be happen, fib 4 and fib 3. Okay. Now this is the new problem. You can see when we are calling this fib method with 4 input, it will call again with fib 3 and fib 2. Okay, so n minus 1 and n minus 2 we are calling in this method. You can see, okay, n minus 1 and n minus 2. Now again, so when we are calling this fib 3, it is again calling fib 2, fib 1. Okay, now this problem is again calling fib 1, fib 0, and from here we are returning value back 1 and 0 because we have reached at the base case. So in this way, now each call is now separate new call, and it is expanding further. So okay, so now this 2 is called again further. So this is now calling fib 1 and fib 0, and from here it is returning the value. So same times you can see we are calling this call is actually expanded like a tree things, and where the same problems you can see is repeating multiple times. So like fib 4. Okay, now this is not repeated, but fib 3 you can see it is repeated here. Okay, so if you have solved this, suppose if you get the answer of fib 3, here you are again calculating this fib 3. Okay, now you can see fib 2 is repeated 1, 2, 3 times. Okay, and fib 1 is repeated many number of times in this. Okay, and each part is actually repeating multiple times, and that is called as a overlapping sub problem. Okay, here we have the overlapping of the sub problems. So in this way, it will expand to the 2 to the power n type of times. Okay, so the complexity of this recursive method will become a 2 to the power n. So this is one method to solve this. You will get the answer by this method, but the repetition of the same thing is happening in this process. And there is another way. So what we can do, we can use the we can store the result of the problem. So like suppose call is happening like this, so we will move to this part, and after that we will repeat, we will back. Okay, so now we have solved this fib1 at the first time, and we are returning back. Okay, now we need the another call in this part, so this fib2. So this we have get the answer for this 1 and 0. Now after receiving the two input 1 and 0, we are getting the final answer for this fib2, that 1 plus 0 1. Okay, so now we have solved this. So can we store the solution of this fib1 call and fib0 call and fib2 0 call? Once if we have solved this, at any point if we have solved this problem, just store the result in some place. At any time if this call happens again, first we will check the in our memory. Okay, in our memory we will check this if this sub problem is already solved or not. Okay, if we have the solution directly of this problem, so we will not further solve that, we will directly get the solution from our memory. Okay, so here we can use this our dictionary things, where we can directly fetch the answer in constant time. Okay, so you can see we get the answer for fib2 and we will return back and fib3. Okay, so now fib1 is calling again, so no need to solve this. Here this is the base call, so it will return answer no problem in the constant time, but it will not further expand. So now you got the fib3, and same way you will get the so fib4, now you're calling to this side. Now fib2 part is already solved here, so you can directly get the answer for this. Okay, so in this way no need to expand lower side. Okay, from this call you can directly return the answer without going further down. Okay, now this fib4 is solved. Now when we are coming here, so we will not solve this fib3, so that means we will not call further. We will directly check in our memory if we have fib3 solution is already available. Yeah, we have already done these things, so we will directly fetch the answer for this problem, and we will use and we will return back from here. Okay, so that means we will not further repeat the same call, same sub problems again. So in this way we can reduce the repetition things for these problems, and we can solve these things in order of n time. So that means we need only order of n calls for this.
Yeah, this problem, the way you are saying, this will be coming into picture only when this program is in execution for multiple time, right?
No, this is the one time call. This is the one call. This is the simple one call. We are calling fib rec 5. We are giving the 5 input in this problem. After that, it is expanding like this. Okay, so when we are calling, so this is a recursive call. So now recursive call is happening like this. Okay, so these many number of recursive calls are required when we are calling with this 5 input. Okay, but but we can save the computation by just storing the result of sub problems. If we are solving any sub problem, so suppose if we will start the solution from base part, okay, so fib1 fib0, we will store the result for this call directly. Okay, so if we are getting 1 input, we are getting 1. Okay, and we are getting 0 input, we will store this result. After we are calculating this fib2, so this is the addition of fib1 and fib0, so 1 plus 0 1. Okay, so the solution for fib2 is 1. So next time we will, when we are calling this thing, so fib2, we will not further call the another recursive call next part. This fib1 fib0 we will not call, we will directly check from the memory if we have the solution for this input or not. So if we have already done this before, we will directly get from the memory and we will use the solution we will return back without calling further. Okay, so same things here. You can see when we are when we require this fib3, so we will check the solution. Do we have solution, and do we have solved this before? Yeah, we have solved this things here. Okay, so definitely the solution of the fib3 will be available in our memory. So we will directly fetch the solution and we will return directly back without calling further. This fib2, fib1, this thing.
Here we are not implementing any logic. So we are using the Python inbuilt Fibonacci series, right? And it has the logic how it has to give that number, and that is based on that it is generating this in memory. Is it like that?
No, what you are talking built-in function any?
Yeah, because what logic it is So we are telling that we are, if it is less than 1, return 1, I mean return n. Otherwise, you call this function recursively n minus 1 and n minus 2.
Hmm.
So what, there is no logic implemented. Now this is,
No, you are saying that this is not correct.
no, I'm not saying it is not correct. What I'm saying is, to get this Fibonacci series, whatever number we are giving, it is calling that by reducing to -1 and -2 and giving the addition, and then that is how it is forming the number, right?
Okay.
So that is what the logic. There is no other extra logic for this.
No, here we are discussing about the multiple solution. Okay, so this is the one possible solution for this problem. Here our goal is to find out the nth number in Fibonacci series. So we can solve this problem by this method. This is the one recursive possible method. Okay, we are just trying to understand the dynamic programming approach things.
Okay.
So now this is the naive solution. We are using this recursive method, and we are showing here how many calls are required to solve this. Okay, so you can see this will be expand like this. So our calls will expand like this. Okay, these number of calls. But can we save these calls, and when can we stop the calls further if we have already solved one calls? Okay, so there is one method is memoization. So memoization method is said that we will store the solution of sub problems. Okay, and if that sub problem repeats again, we will directly use the solution. Okay, without solving again, without computing again from the scratch.
Sir, this is for the repetition, right? This one, the memorization, and this is for the, if the call is happening repeatedly, right? Happening repeatedly, right? No, I'm asking, is it like,
okay,
yeah,
here, so here we are just giving the example how we can save the solution of sub problems and how we can use that solution later. Okay, without calling the all that, without computing again that part. Okay, so here you can see how this will work. So now if we just see this approach, this dictionary we are maintaining, where the name of this dictionary is memo. Now what we are doing, we are checking, this is the base, if n is less than equal to 1. Okay, so we will directly fetch the answer. So this mom n equal to n. So this is the base condition for this problem. If n is less than equal to 1, we directly return the answer. This is the step. But if not, if n not in, so you can see we are checking this if it is not in the memo. So memo means first we are checking if our n value is exists in memo or not. If not in memo, then we will call recursively. Okay, if it is already in memo, so we will not call this recursive part. We will directly return the answer here. Okay, so that means recursive part we are only calling if our that input n is not solved before. So here you can see in that calling again. Okay, so if we are using the same method, here you can also see we are using the recursive method, but we are storing our result. Okay, so here we are storing the result in our memoization table, memon. Okay, so how it will work actually, you can see this table we are maintaining memo, and where this is actually a dictionary key, and this is the value for that. Now you can see when we are calling this function 5, so this is moving to this side. Okay, in every call we are looking that if our answer is available or not. So initially this memo table is not filled. Okay, so the solution is not available, so dictionary. And now this is the first time call, this is the first time call recursively. Now we have reached at this. Okay, here this is the base case of the our function, so we will directly return one answer. Okay, now from the base call. At that time we will store the result. Okay, so we will store the result in our dictionary, so that answer for 1 is 1. Okay, now when we are moving back, so this is the second part. Okay, so this is the second part of this n minus 1 n minus 2. So from here we are getting 0, so we have written the we have get the solution for this, so we will store in this in our dictionary with 0. Okay, next time we are getting 1 plus 0, we will store here fib2. So for 2 input, we are getting the solution 1. So we will store this in our dictionary. Okay. Now we will move back. Now you can see when we are getting the solution for fib3. So we need fib2. Okay, we have already done this. And now we need fib1 also. So solution of this part, fib1. So we will directly check if the solution for 1 is available in dictionary or not. So yeah, this is available. We will directly read the solution from here 1 and we will directly return back. Okay, now we get the answer for fib3, so that we will store in our dictionary. So that is 2. So we will store here. Okay, after that we are moving back. So fib4 is required, fib3 we have done. Now fib2 is required. So we know we will not call again. Okay, we will not call again further for fib1, fib1 and fib0. Okay, because this solution for 2 is already available in our dictionary. Okay, so solution for this fib2 is now 1. We will directly fetch this answer 1 and we will return back from here without calling this part again. So this part is now reduced. Okay, so same things. Now first time we got the solution for 4, we will store in our dictionary. Okay, now next time when we are calling this fib3, now fib3 is already done previously 2. So we will directly return the answer back. So in this way, sorry. So in this way, we are just saving the computation if we are getting the similar computation again. So we have done that first computation. If previously we have stored the solution in our dictionary, at any time that the same computation is required again, so we will get the solution directly from our dictionary without solving again. So that means the lower part is not required now to call again. So in this way, you can see we are reducing this lower part, lower calls. In the previous tree, you have seen this. So by using this memoization thing, so that memoization just according to the name. So we are actually storing the solution of some sub problems. Okay, if the same computation is required again in our problem, so that we will directly check the solution without computing again. So this is the smarter way to reduce the computation time to solve this problem. So this is the one way to solve. That is called as a top-down approach. Okay, so that is called as a top-down approach, where we are calling from the top down problem, and like this we are using this recursive method, and then we are solving the problem from the main problem. Then we are just dividing that problem into sub problems and like this. So we are solving this problem in top-down manner. So that is called as a memoization things. And another version, we have the dynamic programming. So now this is called as a bottom-up approach, or sometimes and in dynamic programming main things, we also not use this recursive call, and we try to solve that problem with the help of only this loop or tables, this tables. Okay, and sometimes also called the tabular things. We store the result in tabular. Okay, and that is also same memory things. So what we will do, so same problems now we are solving here, we will also store the result. Okay, but we will use the different approach, and this approach is actually bottom up approach. Here we will our final goal is to solve is that Fibonacci fib5, but we will start from the sub problems directly. Okay, so now what we will do, we will check the solution for fib0 and fib1, because here we know that the solution for fib0 is 0, fib1 is 1. Okay, we know the solution, so by default, so 0 and 1. Now the next solution, if we want to find out the solution for fib2, we need to just add these previous two solutions. So this solution we will store in some place, and directly we will read the solution from this place, and we will get the solution for this one here. Okay, now we want to get, so we are solving this problem by the bottom up manner. So we have started with this sub problem. So fib0 and fib1, we have started from this. Okay, this is the sub problems. Okay, and we are using the solution of this, and we are storing to the next in some place. Okay, so now we got this fib2 solution. So this is one. Now for solving the next part, fib3, we need the solution of fib2 and fib1. So we will directly fetch the solution from here. So this is 1, and from this is 1. So 1 plus 1, 2, like this. Okay, so in this way we are getting the solution. So for 4 we need the solution for 3 and 4. So we are just using the solution of fib 3 and fib 2 and adding here. Okay, and for 5 we are getting the solution 4 and 3. So we will add here. So in this method you can see the code. Now this is simply a linear loop. Okay, so now you can see we have just maintained this list. Initially this have only 0, 0, okay, and 0 and 0 and 0. Okay, so n times or one more time. Okay, so total, suppose if we are taking n equal to 5. Now this table we have started for the solution. Okay, now we are starting that we know that t0 is 0. Okay, so 0, 1, 2, 3, 4, 5, this is the index. This is the index. So we know the solution for t0, 0, and t1 we have mentioned 1 directly. Okay, so this we have updated. Now we will solve this from here. We will just read the previous 2 value, okay, and add this. So 0 plus 1, 1. We will update this value, okay, by this loop. You can see ti equal to ti minus 1 plus ti minus 2. So now we have done the solution till this value. Okay, so now 1. Now for next part, we will just read 2 previous value. Okay, so 1 plus 1, 2. Okay, now we got the answer for this 3. Fib 3, this is the value. Now for the next value 4, we need this 1 plus 2, 3. And for 5, we need this 2 plus 3, 5. Now this is the solution. Okay, so in this way, we are using the solution of previous sub-solution. Okay, every time we are adding 2 value and we are getting the new value. And next time we are using that solution directly without repeating the all things again. So this is the tabular form or bottom-up approach, which is called as a dynamic programming. And this is the efficient solution. Otherwise, the same previous method we have also seen, that is actually recursive method, top-down approach, but that have some overhead of recursive calls. But here this we are solving without recursive calls, so that is more efficient. And this is a linear solution for this. So you can see this this approach is taking 2 to the power n, but how we are smartly reducing this to order of n time. Dynamic programming approach. So this is the 3 way we can see. So that means just figure out that all possibility of the combination for the output, and in that combination, if anything is repeating multiple times, so you can save the solution someplace and use the solution without repeating again. So that is actually a dynamic programming approach. So store the result of sub problems and use later that. Okay, so now this is the basic.
Sorry, sir. Sorry. So if we use this memoization and dynamic, it'll give us the same result.
It will give a result, yeah, same result.
So we can choose dynamic over. Like
so memoization actually have some overhead of the recursive things. Okay, recursive calls. So can we remove this recursive part also? So that is actually bottom-up approach or tabular method. So tabular method where we start from the smaller problems directly. Okay, and we start with the smaller problem and we get the solution for that. And we use the solution to get the another part solution. So like this previous example you have seen, we have started with this fib 0 and fib 1. This is the smaller problem, and we get the solution for next problem. Okay, so fib 2 by adding this previous 2. So by this table things, we are maintaining this information solution. This is called as a tabular thing, so tabular form. So sometimes if we require the multiple dimensions, so 2 dimensional is required, so that become a table. So that we will see the example like in this week. So how we can maintain the result of the Hello.
Yeah, thank you, sir. Yeah, thank you.
Okay, so now this is the one very small example with the different methods. Now moves to the another problems, this grid path problem. So this is the first problem discussed in the lecture. So here you can see the problem is you have this grid.
Just one doubt related to that memorization stuff what you have seen.
Yes.
Just trying to understand let's say we have some bigger problem and some program is in execution for a very long time,
Mm,
and in that we have implemented this code, that memorization dictionary we are using.
mhm,
So it will be there in the execution, right? Basically in the RAM and whatever component, something like JVM, what it will have in Python.
mm.
How it will clear that? I mean, unnecessary, it will leave there for very long. And I'm just trying to understand, okay? I mean, not trying to extrapolate anything too much. Hope you got the question, what I'm asking.
Not much clear, but yeah. So if you're saying that, so why this will run very for a very long time?
What I'm saying is, this is there for some bigger problem. Okay,
Ah,
say
bigger problem. Okay.
something like big execution is happening, and
Ah,
that execution is going on for a long time, and this code is getting called now and then using that main application, main problem, and this code is living in that RAM basically, and inside RAM, that whatever the virtual machine is there for the Python code execution. So my doubt is, like, we are not, I mean, if we implement this way, we are not killing that, na, it will be living there for maybe longer than the required.
so why we are not killing this? We are killing this, na? We are just using this base approach also, and this recursive method actually we are stopping this by this memoization things. We are storing the result. So we are checking this condition. If our result is not stored, then we are calling on this recursive part. So if we are writing any recursive solution, definitely it will stop at any point. So if our function is written properly, okay, if we have properly mentioned our base case in the recursive call, that base case for the termination, so definitely your code will stop at some time, after some time. So why it will run continuously? If your code is not properly defined, if your code is that base condition or termination condition is not properly defined, then it will run for the long time. Otherwise, if you have properly defined your solution and all the condition, after some iteration or some repetition, so definitely your code will stop. Why it will take unnecessary long time?
Yeah, I understand. I just, some thought came in my mind. Yeah, we can move on. Yeah.
So here you can see this previous solution. So like this recursive solution where our calls are expanding like this. Okay, so here you can see when we are calling this function only for 5 input, you can see how many number of calls actually happened. Okay, you can count this for this example. So in this way, suppose if you pass FIB like 100, okay, n equal to 100. Now you can assume that how long actually it will expand in the lower. Okay, so 100 means it will the first call of 99, and on the 99 and this side or 98, and again this side, this is becoming 98 and 97, then this part also 97 and 96. So your tree will become expand like this. So this will become a, how many, if you count total number of calls, so it become a 2 to the power 100, to equal to 2 to the power 100 calls. Okay, here input is n equal to 100. Okay, so you are calling your recursive solution like this, so that number of calls will be happen. Okay, but if you are stopping your calls by this memoization things, so it will reduce only till 100 or something, 100 calls. So you can see the benefits of this. In one solution you are getting this 2 to the power n times calls for any input. Okay, and another solution you are getting only 100 times calls. So this is much better. Okay.
Okay.
Yeah.
And sir, this call tree, by implementation of some code logic, can we see exactly how this call tree is forming?
So you can okay, so I'll show you the demo. One second. So this is week 9. So yeah, this recursive call structure you have, this one, and like just open one Python tutor. Okay, so we have this Python tutor. So I'm writing this code here and I'm calling this for small input. Okay, so that FIB for REC for the type or 5. Okay, and I'm calling this function for the 5 input. Now just visualize the things. Okay, and you can see how the calls are actually happens. So I'm moving. You can see total 62 steps are coming. So how the calls is happen. Now this is the first step, and you can see we are passing this n equal to 5. And at that time we have entered inside this. So base condition is not satisfied. Now we have moved to this recursive call, and here this is now called again on n4. Okay, now when we are moving back, so that this part is actually happening. So this leftmost sub tree path we are coming. Okay, so now you can see fifth and 3. Okay, now fifth and 2, and this is n1. Okay, so which path actually we are taking here? So this clean this. So actually we are coming this path. So this call, then this, then this, then this, then this. Okay, at this point we have reached at this point. Now if you move to the next step, so now we will get return back answer from here. Okay, so this is now we have reached at the base case. Okay, so return 1 directly. Okay, now we have moved back, so now our call is moving back. So this is the another call. Yeah, so that is one n 1 this part, and this is n0 this part. So that means this 2 calls are actually solved. So fib 1 we have written 1, and now we are solving this fib 0. Okay, so now it will return 0 from here. So in this way we are returning things, and we will move back. So yeah, now you can see we have moved to n2 part, and we get the solution for this is return with total value 1 plus 0 1. Okay, now we will solve the remaining part for this n1. So that is actually called this one call now. Okay, so we have solved this part, and now we are solving this side. Okay, then we are again running, so we get this 1 for this 1. Okay, and totally so we will get the solution for this 3 2. Okay, so in this way this is this part is actually executing. So now we got the solution for this 3. Now we will return back. Okay, so we will return back here. Now you can see the how the expand will happen. Okay, so let's move to the next step. So 3 you will get the answer for. Now you can see from 3 we have moved to the 2 side. So now from 4 3 is completed. Now we have moved to the n4. Now it will expand again. You can see again we have extend to n1. So in this way you can see now we will get the return for n1 again and n0 again. So you can see we have already done this n0 n1 one time, but now we are repeating again. Okay, now we got the solution for n4. Now we will move back. So from 5 4 this part we have done. So from 5 this part we have done. Okay, this side. Now we will get the solution for this side. So again you will see this, it will expand further. So when we are moving back, so 3, now it will expand again. So 3 2 you can see 2, then 1 again. Okay, so now from 1 you will return, then 0. So in this way you can see how the return is happening again. Same thing is repeating the calls, and finally we are getting the answer. So our call is happening like this in this behavior, if you are understanding correctly. Okay, so
Yeah,
I hope this
very
clear.
helpful.
So now just compare the memoization things. Okay, so let's see that memoization, how the memoization is actually saving the things. So let's call this memoization function. So I'm just replacing this. Let this go. Okay, and now the function name is that FIP. This is the function. Now you can see the visualization, and we are getting this steps. So initially this number. Okay, so now we are maintaining the this things, and now how the expand will happen. Okay, so n5, then n4, then n3, then n2, then n1. Okay, now we have reached at the base case. Now from n1 we will return back. So now 0 we will return back, and you can see now we got the solution for this 2. Okay, so now we got the solution for 2, and you can see this dictionary, how dictionary is creating. So we got the solution for 1, 2, and we have also stored the solution for this one. Okay, now next time when we are moving from this n3, okay, so you can see we will not so we are calling this n1 again, but we will directly return the answer from here. So, okay, we will check from memory, and we will directly return the answer from n3. Now from so that means this 3 part is completed. Okay, we have got the solution for 3 is 2. So now next time when we will call n2 again, okay, so this will not expand further because we have the solution directly from 1. Okay, so this will not expand to n1 again. So you can see you will directly return back the answer here. So return 1 without expanding further call. So you move back. Now you can see we will get the n3, but we will not expand further from n3. We will directly get the solution from this table, and this will return the directly answer from here. You can see return to directly. Okay, so it will return back. So in this way it is finishing early. Okay, so now you can see the solution, how many steps it will reduce. So for the longer input, so let's see. Suppose if I'm taking 100, so let's see how many steps are coming. Oh, stop, since you can see it is taking still last steps. So 50 function stacks. Okay, so there is some limitation for this tool is, or let's take some smaller value, only 10. Okay, 110 steps. Okay, but if suppose if I use the another version, you can see 7110. Okay, so now you can see the difference. So in the for the input 10, if we are following this basic recursive method, we are getting total 710 steps to solve this. But if we are using the memoization method, we are getting only 110 steps. So you can see how much we are achieving. Okay, and so next is the simple iteration method. So that is only one single loop. So it will reduce more time. Now this is the memoization, that this one. And okay, so we have n, yeah, this. So only 26 steps are required to solve this. Okay, so you can see the difference of the different solution. So how we are reducing the steps by this storing the solution of sub problems and performing this. So now this is the first example. I hope this is clear. Another problem, we have this grid path. Okay, so dynamic programming problem, grid path problem. And this problem, actually you can see what is the problem. Okay, so we have one grid. Okay, and we have some starting point, and so we have one starting point. This one, this is 0 0, and this is a 5 0. Okay, 5 0. So like this is the way to write. So 0 1 2 3 4 5. Okay, and this is 0 1 2 3 4 5 6 7 8 9 and 10. Okay, so this is the grid, and we need to figure out the path. Okay, so 0 0 to 5 1 0. So how many paths are possible for this? So we can either move to the right, okay, in one step, or we can either move to the up in one step. Okay, we cannot move to left or down. So this is the condition for this problem. we have only this condition, we can move to the right one step, or we can move to the up one step. Okay. So with this condition, how many paths are unique paths are possible to reach from the 00 to 510? So these are some given possible like paths. Okay, so this blue line, yellow line, red line. So how you can solve this? Okay, so this is one problem, and how you can solve this using the dynamic approach or that memoization approach. So what you can do, you can write the solution for this smaller problems here. Okay, so we will solve this by the smaller problems. So how you can get the solution like this. Okay, so for the first path, okay, so like this path, if we are just moving to this path, so at every point we have only one path possible. Okay, so we will write 1 1 1 here for each value. Okay, similarly, if we are moving to only this first line, that 0 line, so that means only one path is possible. Okay, because you can only move to the right or move to the up. So in this way, you have only one path possible for this line, and above line is also one path possible. Okay, but now we will use this base condition. So now we are assuming that this is the sub problems. We have the solution for sub problem solution. So if we have only this path, suppose if we are finding out the solution for that 0 to this 5 comma 0. Okay, so what is the solution for this 0 0 to 50? We have only one solution, so one path is required. Okay, so this is the sub problem we are figuring out. So after that, we will use this sub problem solution. Now we have the solution for this. We have stored the solution at each point. Okay, so we have the solution for this point, like this. Now we will use the solution to find out the solution for a bigger problem. Okay, so now we want to find out the solution for this point. So how many paths are possible from 0 0 to this that 1 1 point? Okay, 1 1. So how we can achieve the solution for this? So you can see we can come from here, okay, and we can come from this side. So now two paths are possible. So that means one solution we are getting from this side, and one solution we are getting from this side. So, and we have also solution of sub problem here, this one and this one. So we can simply add this left point solution and right point solution, and we can add this. We will get the answer for this point. Okay, so 1 plus 1, 2. Two solution is at this point. Now for the next point, like suppose if you want to find out the solution for this point, so till this point we have two paths. Okay, so now that means from that two paths we can come to this. Okay, so we can take this 2 value and we can take this 1 value from lower. So 2 plus 1, 3. So 3 solutions are available, 3 paths are available for this point. Now in this way we can simply solve one by row or column by column like this. So for the next point we can see 3 plus 1, so 4 paths is required. Now next point 4 plus 1, so this is 5 paths is required, and 5 plus 1 total 6 paths is required. Now we get this complete solution of this row. Okay, now we will move to the next row, this point. Okay, now we have the solution for this point and lower point. So we will get 1 plus 2, 3. Okay, like 3 plus 3, 6. Now 6 plus 4, 10. 10 plus 5 is 15, and 15 plus 6, 21. So now we are getting the solution of sub problems, and in that way we will get the solution for this point. So you can see the lower table is filled like this. Okay, so here one condition is taken, another condition is also taken in this problem, so that this is 0 point that I'll also mention here, but we are following the same things. You can see we have getting the solution like this. Okay, so after 3 and 1, then 4, then 4 5 6. So in this way we will simply run this loop. So this is running only 5 into 10 times. Okay, so this is simply number of rows and number of columns. So we are just traversing this grid, and we are getting the final solution for this. So this 13, this is not the solution for that main problem. Okay, this problem solution is different. So that solution I think it is not given, but yeah, you will get some value here. So that is actually larger value. Okay, in this way. So this is the one way. This problems looks like difficult if you know this strategy, dynamic programming strategy. Otherwise, you will try something way to figure out that how many paths are possible. So there are lots of paths. Okay. So, but if we solve this problem like this by starting from the base smaller problems, and we will figure out the final problem. So we can complete this into row into columns total in time. Okay. Suppose n or m. So we have n into m time. Okay. So in this way, but the different version of this problem is, suppose if we have any blockage at any point. So in the same input problem, so like this problem, if we have some blockage at any point, like this is blockage, we cannot move from this point. Okay, like this is also blockage, we cannot move from this point. If this is the blockage, then we cannot move from this point. Then how many paths are possible? So in that case, what we can do, we can solve in the same way, but we will consider the zero value at this point only. Okay, so zero value on this blockage point, and then we will solve in the same way. Okay, so we will solve in the same way. So you can see we have take this zero blockage point, and we are solving simply. So, okay, so 0 plus 20 is 20, like 0 plus 56 is 56. So we will use this zero value. So we can solve this type of problem here. Now, yeah, there are some comparison is given in the memoization technique and that dynamic approach. Okay, so complexity. So like this blockage problem. Suppose we have this type of situation. We have this blockage like this. Okay, and we are solving this problem using this dynamic programming approach from starting from this point. Okay, so what we will get, we will solve this complete yellow part. After that, we are getting this blockage point, and we are getting this blockage point, and we find out that all are filled by zero value, and then we are solving this. So in this way, this yellow part is actually completely wasteful. Okay, and after completion of this calculation of this part, there is no used, and then we are getting this zero information here, and this is already filled one. Okay, so there is no use for this computation. So that means time is required n into m by this dynamic programming approach. But if we follow the memoization techniques here, okay, so memoization is just a top-down approach. We will call from this point. Okay, so we are calling that left point, what is the solution for left and what is the solution for down. If we have no solution, then we will move back. Okay, so that what is the solution for this and what is the solution for this. Now, if we follow this approach, memoization and recursive top-down approach, so in this way, you can see this blockage point have direct zero value. Okay, so if we are reaching at this blockage point, you will directly return back answer zero. Yeah, okay, you will not further call to this lower part. Okay, same way you will call here. So in this way, this call will be happen. At time, you will not enter inside this yellow region. If you are using this top-down approach, you will move only this point, and this is now you will get the one. Okay, so 1 plus 0, you will get 1, then 1 plus 0, 1, like this. Okay, similarly here, so you have the solution of here 1 1, and you will call till point this point, and you will get the return back. So you will not enter this side. Okay, and your number of operation is only required this that m plus n. Okay, so you are only just moving this side only one, this part, and only this part one. Okay, so this part is not covered. The total time is required this m plus n using memoization techniques. So sometimes this memoization top-down approach is also useful, like this scenario, but most of the time this dynamic programming is actually more efficient. Okay, so this is the one case we have mentioned here. So where the memoization is more efficient here.
So in this case, there is only two paths from 0 0 to 5 10.
Only two paths are there. Yeah, so you will get here like this, and you can come from this here. Okay, two paths are there. But if you are using this dynamic programming things, you will compute all the all the points, and after reaching at this blockage point, so then all computation is waste. Okay, So that is actually the wasteful computation by the dynamic programming. So that actually is reduced by this memoization techniques, top-down approach. So this is the one problem is discussed. So now we have mentioned, so this solution is not discussed and mentioned in the lecture, but we have included all the three type of solution for this problem. So first is recursive approach, how we can solve this recursive by the recursive method. Okay, so similar to the Fibonacci series. So this is the solution for. So we have also mentioned the barrier point. So you can give any barrier point and you can pass this function. So here we have mentioned the base case and we are calling, you can see we are calling the left part and right part. Left call, so we are starting from the top point. Okay, so if this is 5, this is 10, and we are calling from the top down manner. Okay, so here we are not storing the result. Okay, we are completely calling, simply performing the recursive methods and exploring all the points, all the area. But this memoization technique, we have improved this, and now we are storing the memoization memo table, and we are checking this. Okay, if this points is already available in our dictionary, then we will simply return the solution directly. Okay, if it is not computed before, then we will call this part. Okay, so this is very similar to your Fibonacci that example. So here, okay, so for if we are computing first time, then we will use call this. Otherwise, we will directly return the solution from here. So it will reduce the time. And this is the dynamic programming approach where we are starting from the lower solution. Okay, so that we will start from I0 and J0 point. And we are assigning this base condition for the boundary position 1. Okay, so that means this point we are assigning all value 1 here, and we are assigning 1 here, like this. Okay, so this is the base condition for this, for the sub problem. And after that, we are simply running the loop from 1 to this point and 1 to this point. Okay, and we, if our barrier is there, then we are assigning 0 value. Otherwise, we are simply taking the two left point value and lower point value and directly getting the solution. So you can see this is simply a m into n. Okay, here x and y is given, so x into y solution. And we are not using any recursive call in this. So this is bottom up approach. Okay, we are starting from the lower problems. So yeah, this is the grid problem which is discussed. Now, next problem which is discussed based on this DP, that is actually longest common subword. Now, this is the another version of the DP approach. Here we will use the two-dimensional table. Okay, so to check the all combinations. So here we have actually two strings. Okay, and we have two strings, and we want to find out the longest common subword. So subword means that parts should be meshed continuously without skipping any character. Okay, so longest part of the strings which is common in both strings. So that is actually longest common subword. And here you can see we are maintaining this table for this. Now, this is the example. You can understand that we are assuming the two tables. So like 0, 1, 2, these are the index. And the first string is we are mapping like this. Okay, so from 0 index to 5 index. And same another in strings we are mapping with the another array. So like this. Okay, but now we are also including the one more index. This is dot. Okay, what it is representing dot. Dot means empty strings. Empty strings we are assuming that. Suppose we are assuming that S1 we have, S2 we have. Okay, now this is empty strings. No character is there. Okay, in the both strings. Okay, so then what is the length of maximum common? That what is the length of common substring? So that means if no string is there, no character is there in the both strings, so the length will be 0. Okay, so because of that, if any of the string is empty, you will get the 0 answer for this. Our final goal is to find out the longest common substring length. Okay, if any of the string is 0 or this empty, and any another string contains any character, so if you find out the answer, so that will you will get the 0 answer as a common character. Okay, so in this case we are making this as a base case, this point. Okay, so we are making this as a solution for smaller problem here at this point. So we are assuming that if our string is empty, Okay. Now another string have any character. Okay. So any characters. So that answer will remain 0. Same things. If we are assuming that this string is there is no character, then you will always get the 0 answer for this. So we are filling this matrix solution for this combination. Okay. Now this actually matrix is meant calculating the solution of each possibility, but actually it will not calculate again any part. It will use the solution of sub problem. So now we got the solution of this condition. If any string have is empty and another string have any character, so like A, B, C or empty, you will get the 0 answer. But after that, we will fill this matrix one by one. So we will just check the value for this solution. Okay, for this, and we will smartly maintain the. We will reuse the solution of previous calculation, and we will get the final answer. So like this. Here we are checking the possibility. So suppose we are considering that our strings on this first string, suppose this is the S1 and this is S2. Okay, this side. So now we are just taking character by character. So suppose we are assuming that we have only this one. So this S1 have only this T and this T character, and S2 is also have only this T. Okay. So for this position we are looking. Okay, so corresponding we will check the what character is coming. So that this is 1 character. Both are match actually. You can see both are match. Now continuously things we will maintain. We will add the diagonal value if we found any continuously sequence matched. Okay, so that means our value should be increased like this in this way. Okay, suppose next character is coming in this position and this position, and if we found the same character match, so that means this should be increases like previous was the result for this is 1. We will add 1 more value in this diagonal value and we will get 2 continuously like this. Otherwise, if it is not matched second character, so we will set to 0. Okay, so that we are looking only for the continuation of the matching. So because of that, we will follow the diagonally increment in this. So here you can see when T and T is matched. So we will add in this diagonal value by 1. So that means 1 length is matched. Okay. Now increase the character. Okay. So now we are including. Okay. So not this. Actually, we will fill completely this table. Suppose after filling this, we are looking for this position. Okay. Because here we are looking for the. So this matching can be happen in any position of the first string to the any position of the second string. Okay, so you can see solution is given. So this is matched with 2, 3, 4, and here the that value is 0, 1, 2. So you don't know where this matching will happen in the string. So that means you need to figure out all possibility. Because of that, we are filling this complete 2-dimensional matrix. So now you can see we will look from this also. Combination of this second character, we are assuming that S2 have C and this is T. So which is not matched. So then we will fill by 0. Okay. So in this case, we will fill this complete matrix, complete possibility. So E is matched with this T. No. So this is failed. Okay. So S is not matched, 0. I is not matched, 0. So B is not matched with T, 0. Okay. So now all possibility with this T is done by this column. Okay. Now move to the next possibility. We will fill this second column. You can fill column by column, or you can fill the row by row also. Okay. So C is now matched with this E. No, then you will fill 0. Okay. In this way, at this point you can see when we are filling this C and C here. Okay. So we are just adding 1 in the diagonal value. Okay. So diagonal 1. Next time we are all filling all these value are 0, but when we are looking this E and the same position E this side. So for this position, so now till now C is already matched. Okay, after this E C. Okay, and we are looking this E is also matched. So how many characters are continuously matched? So that means C E is matched. Okay, C is matched. Because of that, we are adding 1 into the diagonal value. So this one. Okay, again this point S and S is matched. So we will add from this point. So this line is actually representing the continuous matching. So this continuously matching may be happen at any point in this matrix. So finally, what will be the final answer? So the final answer will be the maximum value of this matrix. Suppose if you are getting 4 at this point, 4, 3, 2, 1 like this. So that means what is the maximum common substring length is this 4. Okay. So in this way, we are filling this matrix from the base case condition, and we can write the inductive structure for this type of problem like this. Okay. So that means we are following the same rule. What rule we are following to fill this matrix? And we are simply filling if our character is matched. So what we are doing, we are taking the diagonal value and incrementing by 1. Okay, if our character is matched. Otherwise, if not matched, we are filling 0 in this position. So this is called as a inductive structure, which we are repeating continuously to fill this matrix. We are checking this condition. So what you can do for this type of problems, some standard problems are there. So you can just remember this inductive structure, and you can use this inductive structure when you are writing the code for this. So this is very simple code. You need to just run a nested loop, two-dimensional traversing, and just check this to fill this matrix. Just take this condition, okay, and finally return the maximum of the matrix. So that will be the final answer for this. So if you see the code, so what we are doing, we are simply, you can see we have created the matrix, and we have filled this matrix by the 0 at this. So we have created this 0 matrix completely. Okay. We have created the 0 matrix so that last row and last column will be filled by 0. So, but we will start from the this index. Okay, so that fifth and that one less. Okay, so n minus. So we are starting n minus 1. After that, what we are checking, if our character is matched, we are just taking this diagonal lower value and adding 1. Otherwise, we are filling by 0. And in this process, we can also check if our value is maximum to the previous value or not. So we are assuming this is a maximum. If we are getting any value maximum compared to the previous maximum, so we will update this, our maximum. And finally, we will return our maximum answer. So that will represent a maximum, that common substring which have the maximum length in 2 strings. Okay, so yeah, this is one problem, longest subword problems. So you can just take some example and you can go through. You can just take this inductive structure in your mind, and you can apply the one dry run on this example. Okay, then you will get the complete idea how this is working, and you can, after that, you can implement this code. Okay, so in this way we are solving this problem with the complexity m into n. Next problem is the another version of this, longest common subsequence. So subsequence is just a where we can skip the character in the sequence. Okay, so in the previous problem where we cannot skip the character, we have to take the continuous character. But here in the sequence, we can skip the character in the during the matching. Okay, so here you can see the example. We have 2 strings, but in these 2 strings, so S, E, C, and this T is matched with this part, S, E, C, T. So here we have skipped this part, but from left to right and this left to right, this is actually matched. So that is called as a subsequence. Okay, where character can be skipped during the matching. So we need to figure out the maximum length of the common substrings into string. Okay, so same things we will follow, the same tabular form we will use here, and we will set up the base condition like this, 0 and 0 this side, empty case. But here, because we can skip the characters, so we will maintain our previous solution. If our character is not matching, still we will maintain our previous maximum solution. Okay, so here you can see if T and T is matched, so we got that diagonal increment. Okay, but if character is not matched, then we will check that which side we are getting the previous maximum solution. So we will just check what is the so like this value, we will check lower side and this side. Okay, so E and T is not matched, so then we will check this side 1 and 0, which one is the maximum. So we will maintain our previous maximum solution. Okay, our final goal is the total maximum length. So here we can skip the characters. So, but because of that, we will maintain our previous maximum solution what we are getting till that point. So one we will pick here. Okay, so same again, we are not getting the matching, we will pick here. But at any point, you can see now the matching is started at this point and this point. So we will just diagonally increment it. Okay, at this point. So again, next character is matched, next is matched, this point. So if next is not matched, so we will maintain which one is the maximum this side, 3 and 4, 4. So we will maintain 4 here. And for this point, this is not matched, so 3 and 4, which one is the maximum? 4. Okay, so in this way, you can see the inductive structure of this. If our character is matched, okay, or AI and BI character is matched, so we will just simply incremented our diagonal value. Otherwise, we will pick the maximum of right or down. Okay, so this is the right position or down position. So we will pick the maximum if our character is not.
Sir, can you please give some example and what kind of with what kind of problem this to be implemented? Like we are trying to find, right, what is the in a given sentence or some what is the subsequence of the string or character, right? That is what the problem, right? So how to understand this with some real-time given data, like how exactly?
So there is a one big very common problem is actually plagiarism. Okay, so suppose we want to figure out that how much actually two files are similar. Okay, so that is if you have already done med1 and med2, if anyone have done, so you submitted the project. Okay, you submitted the project files and code. So we actually that med team actually run the plagiarism actually application on that submissions, and they checked actually how much the solutions are similar to the others. Okay, so here we actually inside the plagiarism software that this type of algorithm actually used, where this actually longest common subsequence will return a maximum similarity of the file. If your one file contains some text, another file also contains the text. So what is the maximum similarity? And this similarity we are finding out the subsequence form, not randomly. Okay, so subsequence form, suppose if first line 20 words are matched, after that 10 words are not matched, then after that continuously 10 12 words are matched. So that is actually representing the similarity thing, so more similarity. So that we are not looking like that. So if first word is matched with the last word of the another file and second word is matched with the first word, so that type of things we are not testing. Here we are checking the subsequence thing. So the sequence we are maintaining from left to right. That means in the file of the top to down or first character to the last character order we are maintaining. And in this order, how much similarity is there? So what is the length of the maximum subsequence? So that actually represent the maximum similarity of the two files or two things. So that is called as a plagiarism. So that is one example for this.
So something like in Word document, if we, I have a big paragraph and then I do a string search that whether this is found or not in Excel or in code comparison, right? I have a previous code commit version V1 and I have a V2. I compare what is the difference.
Yes.
In all these cases, it will be this mostly.
Yeah, so that is actually another version we have. So this is one longest common subsequence, but the next is the min edit, that edit distance. Yeah, this is also one very common that algorithm which is used to find out the similarity of this. So this is the just a different version of the previous one. So you can also figure out the similarity of this algorithm, and the next algorithm is directly based on that. So this is the one example, string matching. Okay, so that string matching, we have the totally separate week where we actually are looking for the pattern matching algorithms. Okay, where we are searching something. Okay, we are searching some text in our file. So how that matching is actually happens. So that related algorithm we are learning in our week 12 content. But here we are figuring out the similarity level, how much actually the two files are similar or two texts are similar or two strings are similar. Okay, so that things we are figuring out here. So that applications are there, only this plagiarism things, if we want to check the similarity of the two files.
Sir, in this, like in the row, if you have skipped letters, in the column also can we skip, or the column has to be continuous?
In which problem you are saying, LCS or LCW?
In the second one, the
So
whole.
second one, yeah, you can skip this also. So your suppose this SEC is coming at this point. So E and C is coming at this character. So you can skip like this. Still, it will be match. Okay.
Okay.
So that SECT, still it will be match SEC and then T. So that will also be matched because this order should remain same. You can skip the character in between. You cannot match like this. So suppose this is E and this is S. So then this is not matched. Okay. So we cannot change the order. So order should remain same. So S, E, C, T. So this is the order left to right in this coming. So same order should be coming in this.
Okay. Thank you, sir.
So that is called as a subsequence, common subsequence. So only the change we are following this inductive structure here. We are simply storing the previous maximum solution. Okay, we are not putting the 0 value because here we can skip the characters. So because of that, we are not putting the 0 as we have seen in the previous. Okay, so if our any character is not matched, so that means we lost the continuity. So because of that, we put 0. And now if we are matching fine, then we are just picking the previous diagonal solution. Okay, and we are adding 1. Here we are just maintaining the previous solution. So by this maximum of previous matching. Okay, so in this way you will get the final maximum length at this point, 0, 0 point of your matrix. Okay, because here we are maintaining the previous solution. So overall you will get the total this max value at this point, and that will represent your final length of the longest common substring. Subsequence, sorry. Substring is the same of subword. Okay, so in this way you can see the implementation. So same implementation we are doing here, no change. Only this inductive structure is changed and the returning things is changed. So if character is matched, we are diagonally incrementing, otherwise maximum things. Okay, and returning the LCS 0, 0. This is the LCS is a 2D table. Okay, so we are returning this value. So this will return a maximum length. Okay, so here actually this type of problems we are focusing on some optimum value actually. So what is the maximum length actually we want to figure out. We are not figuring out that what is the string actually matched. So for that there is a multiple possible answer. Okay, so if you have 2 strings, here we got the correct answer that the maximum common substring is with length 3. But what is the strings? So for that there may be a multiple possible answer for that. Okay, so here you are getting SEC is matched, but there may be a chance you will get like SET. Okay, so this no, this is not continuous, sorry. Yeah, but there may be a chance you will get the 2 subsequence. Okay, so continuous 2 sequence which are matching in the same. Okay, so suppose in the if you have the long string and the initial part, this is also matched, or up you have some near mismatch character here, and same part is here matched like this, and that also have the same length 3. So multiple solutions are there. Maybe you will get the multiple substrings which are common with the same maximum length. Okay, so you cannot return a exact fixed unique answer for that. So but the length is correct, that is maximum 3. So 3 length is correct. But if sometimes if like this type of question is asked, like just return a one possible substring. Okay, in that case you can return the solution by just revert that backtracking. Okay, so you can just follow the backtracking method in your table and just check the corresponding character for that. So just check that at which point you are getting the max value in this problem. So you are getting the max value at this value point. Okay, 3, 3. So what are the corresponding index for this 2 and this? So you can just read the character. Okay, S. Okay, after that just move diagonally, because you know that we have incremented diagonally value. So just move back diagonally in the lower point and just read the next character at the corresponding. Okay, so E. Or you can directly also recall that what is the starting point at this position. So 3. So this the length is 3. So directly return this 3 length strings. And same thing, suppose if you're getting 3 here also. Okay, so that is the another possible answer. Okay, so you can just read the value, and from that value just return 3 length strings from this point. So that will be also be the answer. So in this way you can return back the answer by just taking the which point actually have the maximum value. But this length is actually fixed. So that type of question is asked, what is the longest common length? So that you can return directly as a unique answer. Same things here, longest common subsequence. So here you can track you can track like this. So with the maximum value, this is the solution. But you have to check the condition here to track the character. Actually, you have to check if both right and left both have the smaller value. If both have the smaller value, then pick the character. Okay, so this condition you have to check to figure out the character which are matched actually. Okay, so here you can see 4, this is 4 and this is 3, so both are not less. Okay, so just skip this and move to the equal value side. Where is the equal value side? So now 4 you have moved, again check 3 and 4, so don't check the character, again move to the next equal side value, and after that you can see the right value and lower value are lower value compared to this. Okay, so at that point just read the character, corresponding character. So this is S. Okay, and move diagonally. When we are reading the character, move diagonally. So now from here just check this, if you're getting the same condition, lesser value, so read the character. Okay, move diagonally, then read the character. Okay, move diagonally. At this point you can see now you are getting this 1 and 0. Okay, so both are not lesser, so just move to this side, move to this side. Here both are smaller, so that means this is the point where you need to track the character. Okay, so the T. So in this way you can you can use this reverse tracking and you can figure out the one possible answer, not the all possible. Okay, sure. But length is actually fixed. This is the correct maximum comma subsequent. Now next is this edit distance. So yeah, this is the more closer to the plagiarism things. So here it is representing the minimum number of editing operation needed to transform one document to other document. Okay, so here one document is given D1, D2. Okay, so that contains some data, that another contains some data. Okay, so what are the minimum edit operation is required? So this D1 document will become same as a D2. So what are the edit operation is? So edit operation, you can insert a new character, you can delete a character, or you can update a character. So these are the 3 operations you can perform as an edit operation. So this is the problem. So like if this example is given that the same SEC, so that SECRET. Okay, another side this has BISECT. Okay, so we have this S1 and S2. Okay, we want to make this string similar to this bisect. So what are the minimum edit operation is required in this? So it become equal to this S2. So here we are figuring out the minimum operations. Okay, so if any strings have this minimum operation is value is very less, so that means that string is are actually more similar already. Okay, if this number of edit operation is high, so that means the difference is high in the 2 strings. Okay, if edit number of operations are less, so that is representing that both are more similar. So here you can see what we can do, how many number of operations are required to perform this. So the same thing, so SECT, so SECT we have. Now we have to corresponding, so we have to maintain the sequence here. Okay, so what we have to perform the operation, we have to remove these 2 characters. Okay, we have to remove this 2 characters, so these 2 operations are required, delete. Okay, so now it become a SECT. CT. After that, we have to insert these two characters. Okay, at this point. So BI. So now 4 operation is required minimum to convert this first string into another string. So this is just to understand edit operation and how we can figure out this edit operation for 2 strings by the algorithm. So here our goal is to find out the minimum number of edit operations. So we will maintain our minimum solution where from we are getting the minimum operations. Okay, so you can see now to fill this matrix. Now the base condition. Okay, so base condition, how we will fill if any string is empty and another string have contained some character or empty. So if another string is also empty, so 0 edit operation is required. Okay, but if this is empty and this have only T character, okay, so that means 1 operation is required to update this. Okay, so you have to insert 1 character in this to make equal. If this have 2 character, so that means you need to insert 2. So 2 value is required, 2 solution is required. For this R till this R, so 3 edit operation is required. Okay, so we are assuming that 1 string is empty, so that means 3 insertion operation is required. So in this way you can fill this completely, and same way you can fill this. Okay, so just assume that this is empty. Now this you are assuming the character including, so that you can getting a solution for smaller problem. After that we will utilize this to get the solution of another problem. So now we are taking this first character and we are comparing this character. Okay, if our characters are matched, okay, so in this case if characters are matched, so that means no edit operation is required. So we will follow this diagonal, we will directly read the diagonal value. Okay, so AI equal to BI. If character are matched, we are reading the diagonal value, we are not incrementing or here, we are simply reading the diagonal value 0 0. Okay, if character is not matched, so in that case we will pick the minimum of all these 3 value. What is the minimum solution, minimum number of edit operation we have the previous sub problem. Okay, so that we are looking here. So yeah, and we will add 1 more. So that means now we need to update the 1 more operation. So what is the previous minimum solution we have from the all side? So that ed diagonal, this is left, this is the right, and this is the left. So all 3 sides, and we will add 1 more after getting the minimum. So we will figure out that what is the minimum value among all these, and we will add 1 more.
So one small interruption. So this plagiarism example you gave for both. So there are let's say the project submitted. Okay, I have submitted a project. Now this we want to analyze whether there was any amount of plagiarism. So it will go for the entire, I mean, how it will decide with which one it has to compare. One is my data set given, I have submitted my project. Now my project will be compared with what is the input range.
So yeah, so that is actually how many submissions are coming. So that we need to compare with everyone. Okay, suppose if 100 submissions are coming in the project, okay, and we want to find out the similarity in between 100 submissions. So that means every file should be compared with another one. Okay, so that one file should be compared with 99 another files. Then we will find out the if any similarity is there, so you will get caught. Okay, so here actually the comparison is required with everyone, every submission. So that happened actually in this submission of MED1 and MED2 projects. So if you are so like 1,000 students are still are submitting, so that means that plagiarism application is working on the all 1,000 into 1,000 comparisons. It takes time, but it actually performs the result.
Okay, so internally it will be compared with the already earlier submitted project and the new one which some student is submitting.
So in general, it is compared with the current project submission, because I think in every term you get the new project.
Okay.
So that is compared only with the current submissions.
Okay.
Yeah, but there is a chance if you are following some previous submission and the same time another student is also following the same that solution. So at that time that file will be matched actually. So that means if both more than 2 students are following the same resource.
Yeah,
And
see,
they are copying
basically,
all the things actually.
I'm trying to understand this algorithm, but the example what you are saying, I understand. We have to write on our own and submit. Yeah.
Okay, so do not try to this, because this is
Yeah.
actually performing on the each submissions. Okay, so we are our team is actually perform this practice on the every
Hmm.
submissions, and in the each term actually many of the students caught this like case, and they actually project is discarded and they also marked as a failed in the course. So do not try to this. Okay, so this type of algorithm is actually working in the background of this plagiarism application. So this ED is actually represent the minimum difference, that minimum number of edit operations. So that is the, if value is very less, that means file is more similar. Okay, if number of edit operations is required less, that is file is already more similar. So that means this value is also represent the similarity things. So in this application, so we are following this inductive structure, and we are, you can see we are already solving the smaller problem first, then we are using the solution of that, and we are getting the final solution. Yeah. Okay. So in this way, we are trying to solve this problem from the smaller sub problem and by some strategic way. So yeah, dynamic programming is not too much easy in the initial phase, but after practicing on multiple problems, so many problems like 10, 20, 30, okay, so you will get a complete idea that how you are approaching the problems, and after that you will get the similar type of problems, and you can conclude the solution. But initially, yeah, it takes time, so because how you will conclude the logic, how you can break the problems, how you can decide to solve the problem from the initial part, that requires some practice. Okay, so try to solve some basic smaller problems for this. So like this, we have this 5 6 example in our this B content in the lecture. After that we have the assignment also and live coding problem also. So total 15 problem I think we have already. And yeah, so this is enough. Otherwise, in the OPP exam, you will get a very small basic problem, okay, where you can figure out. Otherwise, you can also apply your recursive approach if you are not getting the correct logic using the dynamic programming. So we are not restricting anything. So yeah, this is ED, that you will get the final solution. So same things you can see we are following the thing, but here we are filling the base case by the value, okay, not that simply 0. So that we are filling by this m minus I and n minus 6. So same 1 2 3 4 5 6 like this, and after that we are following the same inductive structure. So this is the important things for this type of problems where we are maintaining the two-dimensional comparison possible solution. Okay, so we are just calculating the solution of all possible combination, but in smarter way. So that is also takes m into n time. Now the last problem, we have this matrix multiplication in this week. And what is the matrix multiplication problem is actually, first we have to understand that. After that we can come up with a solution. So what is the matrix multiplication problem? So suppose we have some matrix. So I'm taking one small example, not this is big. Suppose we have some matrix, like we have one matrix of size 2 into 3. Okay, and another matrix we have 3 into 4. Okay, and next matrix we have 4 into 1, and this is m1, this is m2, this is m3. Okay, so m1, m2, m3, this matrix we have. Now we want to multiply this 3 matrix. Okay, so at a time we can only multiply 2 matrix. Okay, so now what order we should follow so that our total number of multiplication operation is actually required less? Okay, so what type of order we are looking for here? Suppose we have this m1, m2, m3. So because here for the multiplication, the size compatibility is also required. So that means for the m1, you can see this number of this column should be matched with this number of rows to the m2. Then you can multiply. Okay, and same things here you can see. So we are following the same sequence, and in this sequence multiplication, which matrix we should multiply first? So this is the one possible combination. Okay, and now M1, M2, M3. This is the second combination. So first we will do this, and after getting the solution of this M1, 2, we will multiply with this M3. Okay, like this. So this is the first combination multiplication, then second. And what we can do, we can also perform this multiplication first, and after getting the solution M2, 3, we will multiply with this in the second time. Okay, so order we are changing of the multiplication. So in which order we are getting how many multiplications? So how we can calculate this? So that we can calculate by this directly by the formula. So if we are multiplying M1, M2, M3, okay. So if we are multiplying this M1 and M2, so how many operations are required for this multiplication? So that is actually what is the first value of this 2. Okay, so this is 2 into what is the common value, 3, and into what is this second value. Okay, so 4. So that means this is 2 into 3, and this is 3 into 4. So 2 we will pick, 3 we will pick one time, and this 4 we will pick. So this is representing the total number of multiplication in this process when we are multiplying these two matrices. So this is required actually 2 into 3 into 4. The total number of operations are 624. Okay, and after that, after multiplying this matrix, you will get a matrix of size M12 of the size 2 into 4. Okay, so 2 into 4 size. Now this M3 matrix you have, this is size is 4 into 1. Okay, so you can see we have the compatibility. Now number of operation is required, so 2 into 4 into 1. So that is 8. Okay, so total number of operation is required 24 plus 8, 32. Okay, if you are following this order. Now another order, if we are following like this M1, M2, M3. Okay, now we are performing this multiplication first. Okay, M2, M3. So M2 size is M3 size is 4 into 1, and this is 3 into 4. Okay, we are performing multiplication between this. So now we have 3 into 4 into 1. Okay, so this is now a 12. Okay, now after multiplying this, you will get a resultant matrix 2, 3. That will be the size 3 into 1. So 3 into 1. And here you have now M1. So M1 is 2 into 3. So the multiplication for this is 2 into 3 into 1. So now this is 6. Total is 12 plus 6, 18. So you can see if we are changing the order of multiplication of this matrix, we are getting the number of multiplication different. Okay, so what order we should follow? So we will get the minimum multiplication. So this is the problem of matrix multiplication. So actually, okay, so we have some matrix. Now we need to find out the solution. That means what is the minimum multiplication are required to multiply these matrix. Okay, so how we can solve, how we can get this answer. Okay, so this here you can see we have only two possible order, and among these two possible order we are getting this is the minimum. Okay, so if you have more matrix, you will get a more possibility. So here in 3 we are getting 2. In when you increase one more, you will get a 5 possibility. So among these 5 possibility, you can just figure out that which is what is the minimum number of operations required. Okay, so this is the multiplication, that matrix multiplication problem. And so yeah, this one. Okay, now yeah, so here this is a little bit tricky. So we will maintain this two-dimensional table here also, but the inductive structure for this is looks like this. Okay, so this one you can see. Okay, so we will fill this matrix only. So here we cannot change the order first thing. Okay, so this what value is representing for the rows and columns. So this size is actually same on the row and columns here. So that is representing the number of matrix. So if we have like M1, M2, this M3. If we have n matrix, so we are just taking this index. So okay, so for n index 0 to n minus 1. Okay, so this is M0, M1, M2. Same for here. So we are maintaining this matrix of the how many matrix we have to multiply. Okay, so that way that if we have n, so n by n matrix. But here actually, so yeah, we will fill this matrix only on from the upper diagonal part to get the solution, because here we cannot change the order and we cannot multiply it like this. So from this side, we'll only always pick, we will pick this, maintain this order, and we will pick the order. Okay, so we can take single matrix. Okay, so this is suppose representing m0, m1, m2, m3 like this. Okay, so diagonal value, what is representing that? If we are only taking single matrix, suppose if you have only m0, one matrix you have, okay, and no, you don't have any another matrix. So how many multiplication are required for that? So that means you have only one matrix, so no operation is required. So you will fill this solution by 0. Okay, after that, same things if you have only m1 matrix and no matrix after that, so you have the 0 multiplication required for that, no solution. So you can simply fill this diagonally like this. Okay, and after that, now we will get the more solution. So like now we will increment the things. So now we are assuming for this point. Okay, for this point we will assuming that we have now two matrix. Okay, this m0 and m1, we have all these two matrix now. So now what is the solution for this point? So we will fill that solution here. Okay, same things at this point, we will fill this matrix diagonally. Okay, so next point we will fill, we will assuming that we have only m1 and this m2. Now we have only these two matrix, so what is the solution for this? Okay, in this way we will fill this. Next point we will increment one more, so m0, m1, m2. Now we have three matrix. Then what will be the solution, minimum number of multiplication required for that point? Okay, so to figure out this things, minimum number of operation, we will figure out the all possible solution in the each case. So that means for this three case, we have this possible way. Okay, so we have seen this m0, m1 we will do first and then m2, and or we can do m0, m1, m2 like this. Okay, so this way. Now you can see m0, m1, we are figuring out the solution for this part. Okay, we want to figure out what minimum number of multiplication is required for m0, m1 in this group. We have already done before this. Okay, so m0, m1 we have already done this point. Okay, so we will not calculate again, we will directly return back the answer for this, and we will check the answer for with this m2. Okay, so now this part is done, and same things for this part, we have already done this m1, m2 at some place. So m1, m2 at this point. Now we will directly read the answer for this part, and we will add with this answer. So we will calculate the answer for this complete part. Okay, and among all these two combination, which one is the minimum? And we will put that here. Okay, so now we will repeat this way. So that means every time we are putting any value for the solution here, and we will read the previous sub-problem solution directly without repeating again. Same times when we will put this m3, so we will read the previous solution. So what solution we have got in the previous part, we will directly read. So in this way we are filling this, and finally we will get the overall solution at this point. Top. Okay. So here you can see we are maintaining this substructure. So this is not looking very easy to understand here. But if you follow the one dry run on the one example, you will understand clearly this how it is working actually. So in the first thing, if I equal to j, okay, so Cij, if both are same, so we are putting 0. So this is for diagonal things. Okay, now you can see this example is given. So in first part we are putting this all diagonal 0. Now what input matrix we are taking? You can see this matrix we are taking m0, m1, this one. Okay, so m0, m1, m2, m3, m4. Okay, so this is the matrix, that list of list. So now next thing, when we are putting this point, okay, so next point, so what we are only looking here, so how many number of operations are required at this point? So we will actually we will fill this formula. So we will directly pick the answer for this position, then this position, and we will just add the new calculation here and this process we will do for all these value of k. Okay, so k will be start from I, from I to less than j. So that means if you put this value in this calculation, so you will get a all possible order actually. So what possible order of the brackets, and among all these, which one have the minimum? Okay, then you will get the final solution. So here for this inside matrix, we are calculating the all possible combination solution, and among all these, we will return the minimum one. Okay, and so these things we will only do if our I is less than j. So that means the above part we will only do. So you can see we are directly reading some previous value here in this formula. Okay, so we are not calculating the completely, but we are directly getting some previous part from the matrix C, and we are adding to the new possible combination. So in this way, so like this matrix, so this is M0, this is M1, this is M2, M4. Okay, so now if you are taking M0, M1, so M0, M1, so only one possible, this is the two matrix, you can directly multiply. So in this way, you can see how many operations are required. So 4 into 10, 10, so size is 4 into 10 and 10 into 3. Okay, so you will get 4 into 10 into 3, total 120. So you can see 120 we are getting here. So at this point, you can simply multiply M1, M2. Okay, so this actually 1 and 2 is representing I and J in the inductive structure in the implementation. So that I and J. After that K value, we are looking for each possible combination. So, but is in this diagonally things we will calculate directly by this. Okay, so 1 and 2. So 1 and 2 you have this 10, 3 and 3, 12. Okay, so 10 into 3 into 12, so you will get 360. So you can simply you will get this this row completely. After that you will try here. So you have already solution for this one bracket. Okay, at this time when you are multiplying this, so you will get a directly solution from this point and you will multiply here. Okay, and another possible solution, and you have this possible solution here already, and you will add this with this. So among all these, which one is the minimum? So you will get that value by this inductive structure, and you can put that. So you can see the implementation. So we are following this. So we are figuring out all the possible solution for the k value, and we are returning back the minimum solution. Okay. So in this way, you will get the final this value here. Okay, so this value at this point. So this is representing the solution for M0 to M4, which have the minimum multiplication. Every time we are only selecting the minimum possible solution, so we are getting the final minimum possible solution. So in this way, you can solve this problem also. So otherwise, if problem is given, so how you can directly pick the order and how you can directly get the answer. So here we are doing this problem from the smaller problem to getting the final solution. So in this way, this matrix. So you can just try one dry run by this inductive structure. Okay, just take this one inductive structure and fill this matrix for this example manually, and you will get a complete understanding for this, how this is actually working. Okay, so yeah, this is the matrix multiplication. We have the dynamic solution, and you can see. Yeah, so this is the last topic of this week. So total for 1, 2, 3, 4, 5. Yeah, 5, 6 problem are discussed in this week. So you can practice in this. Otherwise, after that, assignments are there. So this Friday, some more problem we will discuss. Yeah, any query in this?
No, sir. Very exhausting kind of.
Yeah, this is a little bit heavy. So just give some time. So because of that, we make this week 10 free. So you are due to this quiz 2, you can become a little bit free from before the OPPE exam. So just give more time for this week 9 also. Okay, so you can expect definitely one problem from the DP. Okay, so just complete this. Yeah.
Sir, for the OPP in this dynamic programming, are we looking at complexity?
No. We are not looking complexity.
Okay, thank you.
Okay, if any complexity is required, so that will be mentioned in the problem statement. But most of the time, it is checked only for the binary search-based problem. Okay, so but it will be given in the problem statement itself if it is required. Otherwise, you can apply any approach.
So
Thank
from
you.
DP, whatever problem will come, they it will look only for the solution, not for the complexity.
Yes.
Mm,
Okay, so if you are finding that recursive method easy or to apply, then you can also apply that. Okay.
Yeah, sure.
Okay. Okay. So if there's no query, then we will discuss more problem on the dynamic programming in this live coding session. Before that, you can solve all assignments. Okay. So, and TA will also discuss some new problems. Okay.
Thank
Yeah.
you, sir.
Yeah. Thanks everyone. So.